Testing. Hey, good morning, everybody. Quick note about your test on Wednesday. There are one more. I don't remember. One or two more tests I posted yesterday evening. So you go to, this is under content. Where is it? Simon, previous quizzes. Here we go. So there's a total of 3. I think one was already there. It's on the main page. It's on the main content page. So I added 2 more last night. You have solutions as well. Well, I guess that's all there is to say about that. So you have some extra tests to look at to see what sort of questions you might encounter on the test on Wednesday. Basically, you've got some short answer questions and you've got some programming questions to answer. All right, so in the previous lecture, we were talking about implementing equals. Let's see. Yeah, I'm going to review it in a minute, but for now, I'm just going to continue from the slide that we were on. Okay, so one of the requirements of equals, or the third requirement of equals, fourth requirement of equals. 2 objects are equal if they have the same state, or if their states are equal. Okay, so remember what the state of an object is. The state of an object is just the value of its fields, right? So the state of a point object is the value of its x and y coordinates. 2 points can be equal if they have equal x and y coordinates. All right, so the problem that we run into in equals is that the parameter that gets past equals has the wrong type. Right, so remember, in equals, it looks like equals is always public, and it always returns a Boolean. Its name is always equals, and here's the problem, right? The parameter type is object. So for our point2 class, equals is getting a parameter whose type is object. It's not getting a parameter whose type is point2. Right now, here's the problem. We would like to compare the x and y coordinates of our 2 points, but I don't have a point. I've got a big O object. So as part of step 4, we need to tell the compiler, yes, in fact, the thing that we have is a point2 object. So here in Java, you require what's called a cast. Right, so we saw casting when we worked with primitive types. A cast changes or tells the compiler that the type of something is actually something else. So this is what equals looks like, right? Now remember, when you implement equals, it always looks the exact same way every time. Except you might implement it in a different way, in which case it always looks the exact same way for the other type of equals. So for this version of equals, normally you test, right, is this object equal to the object that was passed in? Also remember that when you call equals, so when someone uses your equals method, they're going to write something like, Boolean eq equals x equals y. Inside equals, remember x is this, and y is obj. Right, so let's keep that in mind. Right, so remember step 1 of, requirement number 1 of equals is an object is always equal to itself. Right, so we would like to know, is x and y are they the same object? In other words, we want to know, is this and obj the same object? So step 1, we test if this equals obj, because that's what equals does when you pass in, when you compare 2 references, right? Are the 2 things the same object? If they are, we can simply return true. We can skip the rest of equals. Requirement number 2, if obj is null, equals should always return false, and it should never throw an exception. So here, obj equals null, return false. The never throws an exception part comes from the third line or the third requirement. So the third requirement says two objects can be equal if they have the exact same type. Two strings can be equal, 2.2s can be equal, two dates can be equal, but a date can't be equal to a string. All right, so to get the type of the object, we use the method called getClass. Right, so if the type of this is different from the type of obj, we return false. Right? The fact that we're using obj to call a method is why you have to test if obj is null first. Right? So if obj is null and that if statement is missing, here you end up with null.getClass, right? And you can't use null to call a method. If you do, you get null pointer exception, right? So remember, null is no object. So here you're trying to use no object to call a method, which is not allowed. So the test for obj being null must come before the test of getClass. All right, so if we get past the third if statement, right? So right here, what do we know? Well, we know that this and obj are different objects. We know that obj is not null. We know that obj has the same type as this. And if we're in the point2 class, that means obj is a point2 object. Right, so right here, we know that obj is a point2 object. We now have to tell the compiler, hey, obj is a point2 object. Why do we have to tell the compiler this? Because up here, we told the compiler that obj is a big O object. So now you need the cast. And that's how you write the cast in Java. Right? You take obj, in front of it, inside brackets, you write the type that you want to cast to. So here it's cast to point2. This will always work, assuming you get past the third if statement. Right? If this if statement is missing, or if you put it in the wrong place. So for example, if you put it after the cast, after the cast, and obj is not a point2 object, you get a class cast exception here. So in other words, the language will in fact test, is obj actually a point2 object? If it is, the cast happens successfully. You can now store the result in other. Right? So now I know that other is a point2 object, or other refers to a point2 object. Right? And now I can use other to look at the x and y coordinates of obj. Okay, so there is a recipe for testing if two objects have the same state. I'm going to skip over this slide for the time being. I'll come back to it in just a second. All right. So this is the quote unquote correct version of equals. But what you want to do in this next step here, so after you do the cast, is you want to look at the x and y coordinates of obj and other. So conceptually, what you want to write is something like so remember, I want to compare the x and y coordinates of other and this. So I want to write something like if this dot x equals other dot x, and this dot y equals other dot y, return true. Great. Like that. Right. So compare the x and y coordinates of the 2 points. If they're the same, I can return true. If they're different, I'm here, so I can return false. That. And away you go. So that's what you want to write. Do you have a question?
So on the click, you said it's not covering this.
The message, the announcement on OnQ tells you very clearly what's covered on the test. So refer to the message on the announcement on OnQ, and it tells you everything you need to know.
It says that it covers till 13, right?
That's what it says. So that's what it covers.
How about 14 and 15?
It does not say 14 or 15, so it will not cover 14 or 15.
Last year it covered everything.
Yes, but we're not at the same point as last term or last year. All right, so what is this nonsense then up here? Right, because this nonsense looks a lot more complicated. All right, so let me back up. Okay, so this nonsense comes from the recipe for checking if you have equal fields. If your fields are a primitive type and they're integers or booleans, just use equals equals. So in other words, write something like this, and away you go. The problem happens when you have fields that are a floating point type. So if you have a float or a double, you technically correct. The correct version is not to write this. Although if you wrote this on a test, you would be fine. So I would mark this correct on the test. Right.
We mean that, like, if, what you mean, if this x equals to other s, that's me, what does this mean?
This is comparing the x and y coordinates of 2.2 objects
For on overwrite,
for equals.
I can't go write this on the test.
And write this on a test and you would be fine.
Oh, really?
Yes, really. For this particular example, anyway.
Then I.
Okay, so the problem that happens if these if your fields are of floating point type, and it's because floating point numbers are weird, right? So the weird thing about floating point numbers, is there a slide here? Yes, is that this value, not a number, exists. Right, so remember, not a number means that you've done some calculation with your values and you've gotten a result that is mathematically not sensible. So typically it means you've divided 0 by 0. The floating point standard says if you compare an and to itself, you get false. The reason it says this is because it wants you to catch the mistake as soon as possible, right? You've got not a number, you shouldn't be using this for anything. So comparisons of, it's defined so that not a number is equal to nothing, not even itself, right? And this is problematic in equals, right? Because you can imagine that nan might be a valid state for your object, right? It might be okay for a 0.2 object to have coordinates that are equal to not a number, right? It simply indicates that you've divided 0 by itself, right? Or done something weird with infinity or something like that, right? This might be fine as far as you're concerned for your implementation, right? The problem is if you write this and you've got 2 points that are not a number, right? This returns false, which you probably don't want, right? So that's no good. Similarly, the floating point standard says that -0 is equal to 0. However, the Java language says all doubles, that all floating point values can be sorted in a sensible order, right? So if you can sort stuff, if you can sort double or floating point values, what that means is that -0 is less than 0 as far as the language itself is concerned, right? And so you want to be able to catch the case where you're comparing 0 and -0, right? For your purposes, you might want this comparison to be true, in which case you should write this. Right? But the recommended way of checking for this is to not let them be equal, right? In other words, you want them to indicate that there is a difference. In particular, the sign is different. So you have to do something else. You can't be equal. Please turn off your phone. All right. So how do you make these tests? So how do you actually do these tests if you want not a number to be equal to not a number, and if you want -0 to not be equal to 0, right? And so the answer is, well, you can't use equals, you have to do something else. So the something else that you do is you use this method called double to long bits if you're comparing doubles. You use this method called float to int bits if you're using float. Right? What do these methods do? Okay, so remember that doubles and floats, these are just values on your computer, right? That means they're just a sequence of zeros and ones. Int in Java has the same size as float, so they both occupy 32 bits. Double and long have the same size in Java, they're both 64 bits, right? That means they're both just a sequence of 64 zeros and ones, right? And so there's a method that converts a double value, looks at the bits of the number and says, okay, the bits of this number are the equivalent long value, right? So in other words, it takes your bits of your double value and reinterprets it as though they were the bits of a long value. Right? All long values are comparable to one another, right? Because they're integers. So no two long values are equal. That gets you -0 not equal to 0, right? So when you convert the double value that's -0 to long, it's a different long value than when you convert 0 or +0 to long. Similarly, if you convert a double value that's equal to nan, that has a well-defined bit pattern. That means it's equal to some long number. So you end up, after you convert double nan to long, that's equal to double nan to long converted to, double nan converted to long. So you now get nan equal to nan. And so that's why this recipe recommends performing steps 2 and 3 here. Right. So that's the very long-winded explanation of why you should write equals this way if you're comparing floating point values. Right. For the purposes of this course, go ahead and write it this way. Everything will be fine. Yes.
Well, if you said if I don't write it, it should be fine.
No. So I'm saying for the purposes of the test, this is too complicated. Right. This is not. I don't care that you know how to do this in this course. Right. That's not what I'm testing. If I'm asking you to implement equals, I want to know, do you understand what the 4 requirements are of equals and how do you implement them? Okay. So this is the correct way to do it. So what is this? How does this work? Well, it converts x and y. Sorry, it converts the x coordinates to their equivalent long values, right? And compares them. If they're different, it immediately returns false because your x coordinates are not the same, right? It then does the same thing with the y values, right? Converts both y values to their equivalent long value. Right? If they're different, it immediately returns false. If you get past those 2 if statements, you know that the x and y values are the same, so now you can return true. Right, and away you go. Okay, I guess let's go back to this recipe quickly. So this is the case. So the 0.2 example is the case when you have primitive fields. If you have reference fields, you should use the equals method to compare your objects. Right. So if you had, if x and y were references, you would use x equals, this x equals other x, and this y equals other y to compare them. Right. So that's the purpose of equals. Right, it's to compare 2 references for equality. Sorry, it's to compare 2 objects for equality. If you're comparing arrays, you can use arrays equals. You can write a loop, compare all the elements of the arrays yourself if you wanted to. Okay. Any questions about comparing the state of 2 objects? Right. The idea is pretty simple. You just compare the corresponding fields of both objects to one another. Right. As soon as you find a pair of fields that are different, you know the answer is false. Right. That's the simplistic way of looking at equals. Okay. So what does our version of equals do? It compares 2 objects for equality. Right. If both objects happen to be 0.2 objects and they happen to have the same coordinates, those 2 points are considered to be equal. So for example, here's the point -1, 1.5. Ignore the f. This is a copy and paste error. If I make a copy of point P, then Q also has the coordinates -1.0 and 1.5. Right? Are they now equal? The answer is yes, they're equal. Right? They're different objects. Right? New 0.2 here, new 0.2 here. Right? So they're different objects, but they have the same state. So now, when you compare them, equals returns true. Okay, so the 4 requirements for equals, they actually have a mathematical description, right? And the mathematical description is the following. Right? So equals is reflexive, symmetric, transitive, consistent, and it must not throw an exception when passed null. These are all terms for mathematics, right? So what does reflexivity mean in mathematics? So in the case of equals, it means an object is equal to itself. Right? So x equals x is always true. Symmetry means if you flip the order of x and y, it doesn't matter. Right? So in other words, 2 objects must agree if they are equal. So x equals y is true, if and only if y equals x is true. Right? So if x equals x is false, then y equals x is also false. Transitivity simply means that if you have 3 objects, and they all think they're equal. Sorry, if you have 3 objects, the first 2 think they're equal, and the second 2 think they're equal, then the first and the third are also equal. Right? So if x equals y is true, y equals z is true, then it must be the case that x and z are also equal. Right? So x equals z is also true. And finally, consistency means that equals is not random. Right? So in other words, if you compare x and y, and you never change the state of x or y, then the answer is always the same, right? So either the result is always true or the result is always false, as long as you don't change the state of either object, right? If you change the state of the objects, then the result can change. And finally, the last part, step 5, is what's called non-nullity. right? X equals null is always false, and it never throws an exception, right? You are not supposed to write null equals X, right? So symmetry doesn't apply in this case, right? Remember I said symmetry means that if you flip these two around, you get the same answer, right? The exception is when you pass in null, right? Because you're not allowed to write null equals X and expect it to work anyway. Right? So symmetry doesn't apply here, but it does apply everywhere else. Okay, so if you look at the documentation for equals in the object class, you get this definition here, right? So it spells out in great mathematical detail exactly what equals is supposed to do. Right? If you follow the recipe that I showed you for implementing equals, it turns out you're guaranteed that all of these are true, right? And that's why the recipe exists, right? It's there to ensure that you always make sure, it's there to ensure that the 5 requirements of equals are always satisfied. Okay, so let's do one more example of equals, right? So let's implement equals for a counter. Right? Remember, a counter just keeps track of a value, of an integer value. So how do you implement equals? It always starts the exact same way, right? It's always public Boolean equals object. Right? Step 1, you always compare this to obj. Right? So if this equals obj, the answer is true. Right? They're the same object. You're comparing the same an object to itself. Right? So reflexivity requires the answer to be true. Non-nullity requires you return false if obj is null. So if obj is null, return false. Right? Now go back to our original recipe. Only objects of the exact same type can be equal. Use getClass to get the types. Right? So this getClass is not the same as obj getClass, return false. Now that we've gotten past the first 3 if statements, we know that obj is in fact a counter. Now you use the cast. Right? So take obj, cast it to a counter, store the result in a variable called other or o or whatever you want. Right? Okay, so now we've finally got a counter reference that I can compare to this counter's value. So now just compare their values. So if the 2 values are equal, the result is true. If the 2 values are different, the result is false, right? The counters have different values. Value is int, so I can safely use equals equals here. I don't have to use float to int bits or double the long bits. So it's always the same. It's always the exact same thing when you implement equals, right? The name never, the method signature never changes. The first 3 if statements are always the same, right? The 4th step, where the cast, is always there. The only thing that ever changes is when you go to compare the states of the 2 objects, right? How you compare the states depends on exactly what how the state is represented. All right, any questions about it? So the easiest way to implement equals is to basically memorize up to this line here. You can also ask Eclipse to do this if you happen to be sitting in front of Eclipse, right? If you go to Eclipse and you go to the source menu, there is a generate hashcode and equals option, and it will generate hashcode and equals for you. Right. The problem is if you're sitting in a test, you don't have Eclipse sitting in front of you. So you do need to remember the first 4 steps here. Okay, any questions about implementing this version of equals? Yes.
Okay, so on the quiz that would be not covered, right?
Equals is not covered on the first test, but that means you are guaranteed to see it on the exam.
But not quiz 2.
Not quiz 2. That's correct.
But covered last year.
It was covered last year. We are not at the same point in the course this year.
So is it going to write a constructor message field like that?
You will be asked questions relevant to where we are at this point in the course this year.
Not today.
Not today. Oh, wait, any other questions? All right. Next set of slides. So I guess I have to make a decision here quickly about what to cover in this set of slides.
Equals is covered on the exam. Is hashcode covered as well?
Everything we cover in the course is going to show up on the exam. Okay, so there is a second version of equals. I think what I'm going to do is I'm going to skip the second version of equals and come back to it in a couple of weeks because it's not relevant to our purposes right now. It's only relevant when we talk about inheritance. So I'm going to skip over this version of equals and I'm going to jump to hashcode. I will come back to this though. All right, so if you've done or if you've looked at assignment 4, you'll notice that assignment 4 asks you to implement hashCode in equals. Turns out implementing hashCode is very easy, but you have to, but it's worth explaining to you why you have to implement it and what the heck it does. All right, so there is a rule, there's a rule in Java, if you read the documentation for the object class, that says, if you decide to override equals, you must also override hashCode. Right? The reason you have to do this is because if you don't, anything that relies on hashCode breaks. Okay, so for our point 2 class, for all of our classes so far, we have not replaced hashCode yet. Right? We replaced equals, we haven't replaced hashCode. So in Java, there are what are called hashed containers. So there's something called hash map. There's something called hash set. I didn't tell you about sets and maps yet. Maps are like Python dictionaries. Right? But there are these containers that are called hashed containers. The hashed containers rely on this hashCode method to work properly. So here we've got a point P. Right? So it's the point 1 minus 2. I make one of these hashed containers. So I'm going to make a hash set here. And I'm going to add P to the hash set. Right? So my set of points now has this point P, right? So it has the point 1 minus 2. Right? The sets are useful for testing things like, does the set contain a particular value? Right? The sets also guarantee that they only contain one instance of every value. Right? So no two objects in a set are equal to one another. So I ask the set, excuse me, do you contain the point P? Hopefully the set says yes, because we just put it in. Right? So here it will say yes, I do contain the point P. Now, if you make another point Q, it's a new point, same coordinates as P. Right? And you ask the hash set, do you contain Q? The answer will be false, even though there is a point equal to Q in the set. Right? Yes. I'm going to explain what hashCode is in just a second. Right? The hash, all you need to know for this particular moment in time is that the hash containers use this hashCode method. Right?
It doesn't have duplicated objects.
Yeah, so a set is a set can hold a collection of objects. No two objects in the set are equal to one another. So a set guarantees uniqueness. All right. So this is weird, right? The set has a point equal to Q, but contain says it does not. Okay, so why does this happen? Oops, sorry. All right, so to explain why this happens, I'm going to show you how you might search a collection. Right. Okay, so imagine I don't have a set, but instead I have a list or an array. It doesn't matter. Right. I know that my list or array, it contains only unique points. Right. So all the points have different coordinates. So how do I test whether or not the list contains a particular point? Right. Well, obviously you iterate over the list or array, and you look for an object that's equal to the one you're looking for. Right. So I'm going to write a little method called hasPoint. Right. It takes in a point P. So this is the point that you're searching for. Right. There's your list of points that you want to search. Could also be an array. It doesn't matter in this case. Right. If points contains a point equal to P, this method should return true. If it doesn't, it should return false. How do you write it? Well, you just write a loop. Right. So for each point in the points, if the point is equal to P, notice that we're using equals now, right? Because we've overridden equals. Right. So if point equals P, we can return true. Right. We found a point that's equal to the one that we're looking for. After you process all the points, you know that the result is false, right? We looked at all the points in the list. We didn't find one equal to P, so you can return false after the loop. Right. Okay, so you should know from 121. First of all, you should know how to do this from 121, right? But you should also know from 121 that this is something called linear search or sequential search, right? Or exhaustive search, right? They all mean the same thing, right? For a structure like a list or an array, right? If you double the number of elements in the list or the array, you double the number of potential comparisons you must make. right? So searching a list that's of size 100 takes twice as long as searching a list of size 50 in the worst case, right? Because you have to look at all the elements in the array or list. So in the best case, you look at the first element and it's the one you're looking for, right? So the best case of linear search is O1, right? Complexity O1, right? The worst case is ON. You look at all the elements in the list and none of them were the one that was, none of them are the ones, was the one that you're looking for. So that's ON, right? On average, assuming the thing that you're looking for is in the list, right? On average, you'll look at roughly half the elements in the list, right? Which is also in ON. So the worst case complexity of sequential search for a list or array is ON. All right, so the hash containers are magical, right? So you'll learn about this in SIS 235, your data structures course. So there is a way to search a collection of items and determine whether or not something is in the collection in O1 time, so constant time, right? There are certain conditions in which you can, under which you can do this, right? So assuming you're not in one of the unusual situations, right? I claim there is a way to search a collection of items in O1 time to find an item to test whether or not the collection contains a particular object. So in SIS 235, you'll learn all of the gory details of how these things are implemented. I'm just going to give you a very high level idea of what's going on. So there are these things called hash tables. Right? A hash table you can think of as just being an array or list of buckets. Right? Every bucket can hold multiple items. Right? So in an array or list, each element holds one thing. In a hash table, your elements are buckets. The buckets can hold more than one thing. Right? So here's a hash table that has n plus 1 buckets. Right? They're numbered 0 through n. Okay, so if you've got a hash table, the way these work in Java is you take an object, right? You give it to the hash table. You say, hey, I want to add this object to the hash table. The hash table takes your object and calls this hashCode method. Right? So hashCode returns an int. Right? The purpose of hashCode is to take an object and convert it to some integer value. Right? How does it do it? It doesn't matter how it does it, right? The basic idea is you're going to look at the fields of the object and do something with the fields. And so combine the fields somehow and get back an int result. Right? So you don't actually care how it does this. All that you care about is that hashCode returns an int that maps an it takes an object A, maps it to an int. Right? That int value is used by the hash table to figure out which bucket should it put the object into. Right? Okay. So remember, ints are negative, right? They're signed, so they can have a negative value. The hash table's buckets are labeled 0 to n. So after calling hashCode, the hash table has to do something to the int value to make sure it gets mapped into the range 0 to n. So that's what this red arrow here means. Right? Hash table takes your object that you're adding to the hash table A, calls its hashCode method, does something with the int so that the int is in the range 0 to n. Again, all of these details are discussed in SIS 235. So here, we called hashCode, got an int value. The int value got turned into 2. So the hash table takes A, sticks it into bucket 2. Like that. If you put another object into the hash table, right? So we're going to put B into the hash table. The hash table takes your object B, calls hashCode. Hashcode returns an int value. The hash table turns that int value, in this case, to 0. So it puts B into bucket 0. Right? C gets mapped onto N. Come on. Right? And D, in this case, also gets mapped onto N. It doesn't mean that D and C are equal. All it means is that D and C have the same hashcode. Right? So that gets put into the bucket N. All right. So after you've put all the elements into your hash table, ideally, right, the elements in the hash table, the distribution of the elements in the hash table is roughly uniform. Right? In other words, every bucket holds more or less the same number of items. Right? Roughly. It's not exact, right? Roughly. So here, all of the buckets hold like 0, 1, or 2 elements, which is great. Oh, sorry. Oh. Okay, so now we've put some elements into the hash table. How does the hash table search for an element? Well, it just repeats the process all over again, right? So if we want to know is A in the hash table, the hash table takes A, calls hashCode, does something with the value, turns that into 2, right? So now it knows to go and look in bucket 2, right? Now there could be multiple items in bucket 2, right? And so it now searches, and now it calls equals on every item in the bucket. Right? So here we're searching for the object whose value is equal to A. Right? So here we're going to use A equals and then the object in the bucket. Right? So in this case, it's true. So the hash table says, yes, I do in fact contain the object A. Oops, sorry, that's true. So what happens if we take Z? Right? So Z is a different, sorry, the value of Z is different from A, B, C, or D. Right? So it's not equal to any one of those. So we ask the hash table, hey, do you contain the value Z? Right? So hash table takes Z, calls hashCode on it, does something with the int, turns it into N. So now the hash table goes and looks at all of the items in bucket N. Right? Is Z equal to C? The answer is no. Is Z equals to D? The answer is no. Are there any more items in the bucket? The answer is no. Therefore, the hash table says it does not contain Z. So it returns false. Okay, so assuming you implement your hash table well, then searching a hash table turns out to be much faster than linear search, right? So on average, right, you end up searching for an element in a bucket that holds a small number of elements or a fixed number of elements, right? The fixed is important. So if you are searching a fixed number of elements and the fixed number is not proportional to the size of the list, the hash table, sorry, right, then that turns out to be in O1, right? And so that's how these data structures are able to perform operations like search very quickly compared to a data structure like a list or an array. Okay, so all of this though relies on hashCode working, right? Or hashCode doing what it's supposed to do. So what exactly does hashCode do? Right. So first, remember, where did hashCode come from? It came from big O object. Right. What does the big O object version of hashCode do? It looks at the memory address of the object, or somehow it gets the memory address of the object and uses that or converts that to a hashCode. Right. So remember, it uses the memory address of the object, or it uses the identity of an object to compute its hashCode. Why is that a problem? Right. So here we've got a point P. It's a new point, right? Here is point Q. It's a new point, right? P and Q cannot have the same memory address, right? Only one object lives at any address, so they can't have the same memory address, right? What does that mean? It means their hash codes are probably different, right? So the hash code of P is different than the hash code of Q. Right? The 2 points are equal, right? Their coordinates are 1 and -2. Because we changed the definition of equals, right? But their memory addresses are different. We haven't changed the definition of hashCode. So hashCode for P probably returns a different hashCode than Q. Right? So P and Q are different objects. Therefore, their memory locations are different. We haven't changed the definition of hashCode. So hashCode is going to use the memory addresses to compute the hashCode. Therefore, their hash codes are probably different, almost certainly, but not guaranteed. Right? And therefore, what ends up happening is the hash table probably goes and looks in the wrong bucket when it goes to look for the object. Right? So in other words, when you ask, does it contain Q? Right? It goes to a different bucket than where it put P. Right? And so now it looks in that bucket, it doesn't find Q, and it returns false. Sorry, that's again, that's a cut and paste error. That's the point, not the complex number. Right. Okay, so there is the very long-winded explanation of what hashCode does and why you have to replace it if you replace equals. Right. So we replaced equals for points. Right. Now our version of equals is no longer consistent with our version of hashCode. So now I have to go and replace our version of hashCode so that it's consistent with equals. Right. Okay, so what do I mean by consistent with equals? So what I mean is if x equals y is true, right? Two objects are equal, then it must be the case that their hash codes are now equal, right? If they're not, right? So in other words, if you override hash code, you have two equals objects and they return different hash codes, all of the hash containers are going to break, right? When they put something into the hash table, they will put them into different buckets. So when they go to search for them, they will search in different buckets, right? So if you replace equals, you have to replace hash code so that if two objects are equal, their hash codes are also equal, right? Similarly, hash code can't be random, right? So you can't randomly return an integer value for hash code, right? If it's random, hash tables are going to jump in random locations whenever you ask for or put an object into the hash table. So if you don't change the state of x, x.hashCode must return the same value every time. All right, so how do you generate a hash code? So it turns out generating a hash code is not a simple process. Right? Sorry, generating a good hash code is not a simple process. Right? There is a notebook for hash code that tells you what the recipe Eclipse uses. It's not important that you know the recipe. All that you need to know is that you need to take the fields of your object, somehow convert them to an integer value. Right? Now, when you do this, it would be nice if you have two objects that are not equal, that they produce different hash codes, right? If you think about this for a minute, though, you realize that you can't actually do this, right? So it's not required. If you have two unequal objects, they are allowed to produce the same hash code. So here's point 2. Again, these should be double, right? Not float. Okay, so why can't you guarantee that if two objects are not equal, they have different hash codes, right? So every point has a double x and a double y, right? How many unique combinations of x and y are there? Well, there's 2 to the 64 values of x. There's 2 to the 64 values of y. There's 2 to the 128 values of x and y. How many ints are there? Well, there's only 2 to the 32. Right? So there's no way that I can convert x and y to some int value and guarantee that 2 points that are different, not equal, have a different hash code. Right? There's going to be lots of points that are not equal that have the same hash code. Right? This is what you definitely should not do. Right? You should not override hash code to return a constant value. Right? Why not? Right? So this is always going to return 1. So when you put points into a hash table, right? All the points get put into the same bucket. If you put everything into the same bucket, it's like putting something into a list, right? So now your O1 search becomes ON because you have to search all the elements in the bucket now, right? So this is a terrible hash code. Don't do this. This is also a bad hash code, right? So for values of x and y that are close together, this always produces the same hash code. Right. So imagine you're writing some application. All of your points have coordinates between 0 and 1. Right. This will put all of the points into one of 3 different buckets. I think 0, 1, or 2. Yes. Right. So this will put all the points into one of 3 different buckets. Again, bad idea. Right. Don't do it this way. How should you do it? So there's a class called Big O Objects with an S. Right. This is the utility class that's paired with object. Right? So it contains a bunch of methods that operate on big O objects. Right? That's why the S is important here. Right? Objects has a function method called hash. You can pass as many values as you want to hash of any type. And objects.hash will compute a hash code for you. So if I want to compute a hash code using the x and y coordinates of a point, right, simply pass in the x, y coordinates of the point, and objects.hash will generate a hash code for you. Right. So this is the way you should implement hash code in this course. Oops, sorry. Equivalently, you can ask Eclipse to generate hash code for you. Right. So the Eclipse version of hash code will I think in new versions of Eclipse, it produces this. I think. In older versions of Eclipse, it does something else. Right? So the older versions of Eclipse, you can read that quote there, and it roughly tells you what it doesn't exactly tell you what it does. But it tells you that what Eclipse does in practice works, but is not guaranteed to work depending on exactly what your object is and what you're using the hash table for, and what kind of objects you put into your hash table. Right. And so it turns out doing this operation where you convert an object into an integer value turns out to be very useful, not just for storing them in a hash table, but in fields like cryptography or other things like that, or computer security. This turns out to be a very useful thing. Right? If you know what an MD5 hash is, this is all related to that. If you don't know what it is, don't worry about it. It's fine. Right? So people do study how to generate or how to algorithms for computing hash codes. All that I care about is that you know why you have to generate hash code, right? Why you have to implement hash code, right? When you need to do it, you just write something like this and everything's fine. I guess there's one other thing I should tell you. Okay. You have to be careful about this requirement right here. Right? So if x equals y is true, then the hash codes must be equal. Right? So remember what you do in equals. You compare the fields of an object. Sometimes in equals, you don't compare all the fields. Right? Some of the fields might not be relevant for equals. Right? So if you leave some fields out of equals, you have to leave the same fields out of hash code. Right? So for example, suppose for point 2, we said 2 points are equal if and only if their x coordinates are equal. Right? So 1, 0 is equal to 1, 2. Right? Doesn't make sense, but let's suppose that we decided to do it that way. What happens if you leave x and y in your hash code method? Right? So 1, 0 is equal to 1, 2. When I call hash code, 1, 0, right? And 1, 2, right? Objects.hash is going to produce a different hash code for those pairs of values. Right? So now you have two objects that equal says are equal, but hash code says is not. Right? They return different hash codes. So whatever fields you use in equals, those are the fields you plug in here. If you leave some fields out of equals for some reason, you leave the same fields out of hash code. Right? If you don't, your hash code method is broken. It's not consistent with equals, right? And all of the hash containers now break when you try to use them. It's actually worse than that. If you take your code and give it to somebody else and they use a hash container, now all of their hash containers break and they don't know why, right? Turns out the reason why is because your hash code method is broken. Okay, so that's enough about hash code for today. Does anybody have any questions about hash code? All right, super. So that's it for today. Make sure to show up on Wednesday for your test.
The question says that until 13, that means